Hi. How are you? Okay, how are you guys?
Pretty good.
It's freezing out there today, isn't it?
It is. It's been cold and windy all week.
Yeah, so cold. At least the air is clear. So.
Yeah.
Yeah. Finishing what we didn't do last time. Okay, so I guess we should go ahead and get started. Welcome everybody to today's class. I tried turning the microphone on. If that makes it worse, I can turn it off. Just let me know if there are any issues with the sound. Okay, so we are going to try to wrap up our discussion of statistical inference, and then we'll move on to talking a little bit about time series analysis in Python. It's kind of a fun little topic. We'll look at how to analyze stocks. But before we do that, so just to kind of remind you of what we were talking about last time when it comes to hypothesis tests. We talked about defining a null and an alternate hypothesis, computing a p-value, which is assuming the null hypothesis true, what's the probability that you observe data as extreme as what you do. So a p-value is a probability calculated assuming that the null hypothesis is true. So remember, it's not the probability that the null hypothesis is true. It's, the probability that things go wrong when you do this test. And so actually, if you do enough hypothesis tests, if you just do thousands and thousands of hypothesis tests at a 95% confidence level, you will find patterns. You will reject the null hypothesis, like you will have a type 1 error or false positive error. So that is kind of a problem in the era of big data, where we have so much data and we have so many different tests that we can try. So one thing to keep in mind is just, by the sheer volume of tests that you do, you will make a type 1 error. And so this is called data dredging, when you just do like so many tests looking for patterns. And it can be a real problem, but there are ways around it. One of the most effective being cross-validation, which is something that we'll talk about later in the course. Okay, and so that process is referred to as p-hacking, right? Sometimes maybe people are tempted to do that in their research when they just really are under pressure to find some significant results. Okay. Okay, so we talked about hypothesis tests. Now, confidence intervals are another side to statistical inference. So instead of setting up hypotheses that you're evaluating evidence for, you're creating an interval estimate of a population parameter. For example, a mean, right? You might have a population and you want to estimate the mean of the population. And so you make some interval estimate. You know, I think the mean is between 2 and 5, something along those lines. So let's look at an example so we can see how this goes. Let's say we have a study which is conducted to estimate the preferred height for an experimental keyboard with large forearm wrist support. A sample of 31 trained typists was selected, and the preferred keyboard height was determined for each typist. The resulting sample average preferred height was 80 centimeters. Assuming that the preferred height is normally distributed with a sigma of 2 centimeters, obtain a confidence interval for mu, the true average preferred height for the population of all typists. Okay, so let's see how the CLT allows us to construct a confidence interval estimate for this population parameter. So what does the CLT tell us about the distribution of the sample mean? You guys remember from last time? What did it tell us about the distribution of the sample mean? Yeah.
That it'll be centered around the population.
Very good. Yes, it's centered around the population means what targets the right thing and what shape does the distribution have? Yeah, it's approximately normal. It's centered around the right thing, and that's critical. And then it said that basically the standard deviation of that thing got smaller and smaller as you increase the sample size. Okay, so when we look at the following quantity, sample mean minus population mean divided by sigma over square root of n, okay, so this, well, this has mean 0 because we centered it, and it has unit variance because we standardized it. So the CLT tells us that that thing has an approximately standard normal distribution. Okay. Okay, and so then we can fall back to things we know about a standard normal distribution. We know, for example, that for a standard normal distribution, there's a 0.95 probability or 95% chance of being essentially within 2 standard deviations of the mean, but more precisely from minus 1.96 to positive 1.96. So this is just a property of standard normal distributions, which you can double check. Right, like we double check it here, 0.95, there we go. Okay, so because this is true, that means that with a probability of 0.95, we know that that random variable, x bar minus mu over sigma squared of n, is in between minus 1.96 and 1.96. And now we can do some clever algebra to just rearrange and rewrite this inequality in the following way as a range for mu instead of a range for x bar minus mu. And when we do that, we get that this is equivalent to mu being smaller than x bar plus this error and larger than x bar minus that error. Okay, so what's that saying? It's saying if we create, again, we don't know what mu is. We can't make an interval based on mu. We don't know what mu is, but we do know x bar, we know n, we can approximate sigma, so we can actually make this a number. We can compute this interval, and then we can say that we think the mu lives inside that interval a little bit more precisely. What do I mean by that? I mean that the probability that the interval contains mu is 0.95. Okay, now here you have to be a little bit careful, even with this statement. So one thing to be aware of is like there's a difference in talking about this interval when you're talking about it as a random interval in terms of x bar, and after you've already collected your data and it's just a fixed interval like 2 to 5. If it's a fixed interval 2 to 5, well, either mu is in there or it's not, right? So it's going to be probability 0 or 1 that it actually captured mu. So, but that's not what this means. This means when we think of that interval as random, depending on X bar, then there's a 0.95% chance that it captures it. So basically it's going to work 95% of the time. Okay. All right, so let's talk a little bit now about making comparisons. This is definitely, I think, probably a bit more useful than one sample hypothesis test is 2 sample hypothesis tests, because often you're in the situation, let's say you're evaluating a drug, you have a control group and a treatment group, and you want to compare the two. Was it effective? So this is kind of usually the more useful setup. So we're going to assume that now we have 2 samples, 2 independent samples from 2 different populations or treatment groups. And we're interested in whether there's a statistically significant difference between some parameter associated with those populations, typically a mean or a population proportion if it's a categorical variable that we're looking at. Okay, and so let's say these 2 populations, we're going to call them A and B. So if your variable is quantitative, you're generally interested in comparing the means. That's the most classic thing to do. So let's say we have mu A, mean for population A, mu B, mean for population B. And then we would set up our null hypothesis as mu A equals mu B, and our alternate hypothesis as they are not equal. And similarly, if we had a variable that was categorical, well, that was binary, okay, so some percentage that we're measuring like male, female, you know, you died or you didn't die, something like that, then we would have 2 proportions, PA, PB, and the null hypothesis would be PA equals PB and alternate PA not equals to PB. Okay, so remember that all of the things, all of these quantities appearing in the null and alternate hypothesis refer to population parameters, not your sample statistics, but your population parameters. And we'll evaluate whether there is, whether the null hypothesis is reasonable or whether we're going to reject it, whether we find evidence for the alternate hypothesis. Okay, and so let's also say that NA and NB are the sample sizes for A and B. Okay, we talked last time about the first hypothesis test we did was a z-test, and that's kind of the easiest one to understand in the beginning. But we did see that t-tests are better if you have a small sample size. And so there's really no disadvantage to doing the t-test for quantitative data. It's kind of just a better idea to do that because you have nothing to lose. Okay, so let's see how we would do a 2-sample t-test in Python. Let's look at the following example. So a nursing home records data on the age and gender of its residents who have passed away in the last 5 years. The ages of the 12 female residents and 10 male residents are given below. In the code. Is there significant evidence of a difference in mean age of death for males and females at this nursing home population? Okay, and again, like I said last time, the question asks, is there significant evidence for a difference? Is there evidence for, goes into the alternate hypothesis. So since it just says difference, not greater than or less than, we set it up as a 2-sided test. And null hypothesis is that they're equal and alternate hypothesis that they're not equal. Okay, so now let's say we have this data, say it's a small data set, so we just typed in our numbers. So we have female death age, male death age. We're going to import stdev from statistics. And then I'm just going to run all of the descriptive statistics associated with those samples. So for the females, we have a mean age at death of 82 with a standard deviation of 7.14. Here I imported this stdev, so I could compute a sample standard deviation, which is just slightly different than np.stt, which is a population standard deviation. Don't worry about that. And then how many data points do we have? That's a sample size of 12. The mean for the males was 73.6, standard deviation 3.9, sample size of 10. So those are the summary statistics that you need to run the test. That's all you need to do. And so the function for doing this is t-test in standing for independent samples, because we have two independent samples that we're comparing. So we can just have two options for doing this. We can just input the data sets directly into the function, and it'll run the t-test under the default assumption. The default would be to do a two-sided t-test. So it's going to assume that you've got a not equals in your alternate hypothesis. So let's see what we get when we do that. Okay, this is the test statistic, which you can sort of think of as how many standard deviations away from the mean, what you observed was under the null hypothesis. And then this is our p-value. So what conclusion would we draw here?
They're statistically different.
Yes, that's right. So we see that there is a statistically significant difference in this mean age of death for males and females, right?
So we reject the null.
So we reject the null. Yes, that's right. Which says that they're the same, because they're not the same. Okay, very good. So we see significant evidence of a difference. Females are living longer. We reject the null. If we were doing a one-sided test, we would cut the p-value in half, because this is giving us the p-value for a two-sided test, or we would just tell the function to do it as a one-sided test. You can also import the summary statistics. If you just have the summary statistics available, you just list them: mean 1, standard deviation 1, n1, and then the other ones. Okay, and again, here we get the same thing with slightly different number because we rounded some of the summary statistics. Okay, so that is a two-sample t-test for a quantitative variable. And let me just show you one other example, which would be if you had a categorical variable that you're measuring in your data and you want to compare that between two different populations. In this case, it would be called a two-sample z-test. So let's look at this. In 1954, polio was widespread and a new vaccine of unknown efficacy, I can never pronounce that right, efficacy was introduced. To test this, in a double-blind study, two groups of children were given injections. One contained the vaccine and the other contained a placebo. So let PA and PB be the proportion of children having received the placebo and vaccine injections respectively to contract polio. Okay, so we're going to have a null hypothesis that A is placebo, right? And B is vaccine, so that the percentage of children getting polio on the placebo is less than or equal to the percentage of children getting polio with the vaccine, i.e. the alternate hypothesis, the thing that we're hoping to find evidence for usually when we run these things is that when you have the vaccine, the percentage is lower, right? The vaccine is reducing your risk of getting polio. Okay, so let's see. We're going to run this test with a significance level of 0.01. Let's see, suppose we collect the following data. Two different sample sizes, both about 200,000, but in the group that had the control, 110 cases of polio, and in the group that had the vaccine, 33 cases of polio. Okay, so there is a difference, right? The question is just, is it statistically significant? How should we evaluate how significant of a difference this is? So the function that you want to use for this is called proportions z-test that you can find in statsmodels.stats.proportion. It's kind of a long, so it would be statsmodels.stats.proportion z-test if you write out the whole thing. So hopefully you won't have to do that. And you just define your counts, right? So these are the positive instances that you observe for both populations. And these are the sample sizes for both populations. And then you can just run this test, proportion z-test with the counts and the sample sizes. And here, what do we get? Our p-value, again, is super tiny. So we're going to reject the null hypothesis. So there's evidence that the vaccine is effective. And if we want to be very correct with how we set up our hypotheses, we will take that p-value and we will divide it in half because we had a one-sided alternate hypothesis right there. Okay. Okay, so any questions on that? Yeah.
So you divided it by 2 because it was a one-sided test. So that there was 2 different samples of populations that you're comparing, then it would be a 2-sided test.
So actually, this sort of distinction of one-sided and two-sided tests is really the same, whether it's one sample or 2 sample. It's just how you compute the test statistic is different, but from, the computation of the p-value is the same. And it's like this picture up here, right, where when you have an alternate hypothesis that's not equals, you're calculating the area in 2 different tails. You're looking at the probability that you get an extreme high value and the probability that you get an extreme low value. But if it's a one-sided test, you're only calculating the probability of one of those extremes. So it's like when you run the 2-sided test, you calculate the area on both sides. Then if you want to do a one-sided test, you would just cut it in half because these things are symmetric. It's always going to be the same area for the lower tail and the upper tail. Is that helpful? Yeah, no problem. Let's see, I've got one thing in the, okay, yeah, I just had an answer in the chat, great. Any other questions on that? Okay, one thing that you'll explore a little bit in the homework is something called A/B testing. And this is something that happens all of the time, with big organizations like Amazon and et cetera. So basic idea is when they're thinking about making a change to their web page design, they will, they'll do a test, right? So they'll implement a change and then they'll direct some small percentage of their users to that new page and track their behavior. And then they'll compare with the behavior of the users on the standard site or classic site, or maybe they have several different versions that they're all comparing. And then the idea is basically to let statistics decide, right? Not the designers, but to actually do these quantitative experiments where you just test, you just try out all these different designs and see what's most effective quantitatively. And this was extensively used in President Obama's 2018 and 2012 campaigns to optimize fund raising strategies, et cetera. So there's an interesting article and some interesting episodes on this. So the basic idea here would be, right, suppose your company is developing an advertisement and there are 2 options that the art department develops, ad A and ad B, and you have to figure out which is better. So you randomly, use Google Ads, randomly show 1,000 users ad A and 1,000 users ad B, track how many clicks you get on ad A and ad B, and now you want to make that statistical comparison. So in the framework of what we've talked about, if we wanted to answer that question, is add A or add B more effective based on doing this sort of random sample of 1,000 from each. So what type of test, what type of statistical test would you do for that? First of all, is it one sample or two sample? It's two sample, and then there's two kind of different options there, right? Based on what you're looking at. Oh, actually, that's okay. So I hadn't gotten that far in terms of whether it was one-sided or two-sided. Let me read I'll read the language more closely. But even before that, like, are you talking about means or proportions, right? What are you really measuring here? Proportion, right? Because this is like, did you click on it or did you not? So that's like a yes, no thing. So you're looking at the proportion, you're interested basically in what percentage of people are clicking on it. So it's like the polio example that we did instead of the mean age one that we did. Okay, so cool. So you guys can look at that. I think I'm ready to move on to time series, unless anybody has any more questions. Okay, great. I think we'll get a little bit further in before taking our break because it's still kind of early. Okay, so now we're going to shift gears a little bit and talk about temporal data analysis, and in particular applications to stock analysis. So you can have all of the tools that you need to make lots of money. Right? Okay, so we will, that was a joke, sorry, perhaps in poor taste. We'll do some temporal data analysis, and we'll see how to import stock data using the Pandas data reader Python package. And we'll see how to do some visualization, different ways of visualizing stocks in ways where we can make good comparisons. And we'll talk about rolling means, which is essentially how much do we smooth things out. And then we'll talk a little bit about time domain versus frequency domain analysis. Okay, so, so first of all, what is a time series? Yeah.
I'm gonna guess. Like just a like time split into different sections of this.
That's definitely part of it. A length of time split into increments. And then on top of that, something that, yeah, go ahead.
Data that corresponds with those times?
Exactly. And that's basically the two pieces, right? A sequence of times, usually at regular increments, although it doesn't have to be. And then some data that you're measuring at different points in time. So think temperature, right? Temperature is a time series as you track temperature over the course of the day. And then stocks, because right, as time changes, the value of the stock goes up and down. Weather forecasting. Then when you start to think about it, it's like, well, gosh, everything is time series. So this kind of data really is everywhere. Okay, but we'll focus on the stocks. So prior to the 1980s, banking and finance was considered to be a bit boring, and they didn't really do a whole lot of exciting mathematics. They just kind of like made loans, etc. But this changed a lot, sort of prompted by deregulation of the financial sector, and also sort of this huge influx of tools from mathematics and computer science and higher computing power. And so it's really kind of transformed the industry into the fast-paced and kind of, not boring industry that it is today, where they actually do a lot of complicated mathematics. For example, a lot of the theory behind math finance is based on the Black-Scholes model, and they've developed algorithms which make split-second decisions. And so machine learning and data mining are very important in these industries now. Okay, and then one for just to give you an example, so one type of strategy is called high frequency trading. And that's basically a strategy where you make a ton of trades in a short amount of time based on some algorithm, and is often quite effective, but it can, for example, cause the stock market to crash for no reason if, for example, there's some misinformation, and then from that misinformation, certain decisions are made and things get triggered in the algorithm and it just crashes. So that happened in 2013. Okay, so let's see, first of all, how do we access this data, this stock data? We're going to use Pandas data reader. This does not come with Anaconda. So you need to run this in your command line before doing this stock stuff in homework. So you just need to do a pip install Pandas data reader, and then you'll be good to go. Okay, so let's do our imports. NumPy, Pandas, Pandas data reader, date time, and we're also going to import this function periodogram from scipy.signal for some of the frequency-based stuff that we'll do at the very end of the lecture. Okay. Okay, so here's some information from the Pandas data reader documentation. We're going to use this function pandas data reader.data, and there's also pandas data reader.wb. These extract data from various sources. Okay, so you have, I guess, different stocks, and then you have different sources of information about those stocks. And here are currently some of the sources that are supported. We're going to use Yahoo actually as a source for our examples. And this is the basic structure of how you're going to import the data. So you're going to create a data frame by calling this function from the Pandas data reader, .data reader. Okay, and then basically you're going to tell it which stocks you want. Then you're going to tell it, you know, which source to use for getting that information. And this is time series data. So you're going to tell it from when to when, right? From some starting time to some ending time. So you're going to have a start and an end. And then I'm not actually sure what the rest of that stuff does because it's optional to input. Okay. So these are basically those forming arguments that we'll be using. Okay, so the data source could be something like IEX or FRED or FF. And then we're going to do the starting and ending time. And there's defaults for that too, but we'll actually make that explicit. Okay, and then of course you can, look at the help documentation for dealing with that function, but this is, I think, looking at this example will kind of give you the idea. So we're going to define our starting time with this date time function and an ending time with the date time function. We'll just take a 10-year period from 2010 to 2020. And then remember, what is this web? Well, that's just what we chose to call when we did the import. That's just what we chose to call pandas data reader.data. So we don't have to type that over and over again. So we're just using that data reader function, and we're going to look at Apple stock, and we're going to take data source, Yahoo, and start and end. And then we're going to look, say, at the tail of this data frame and see what we get. Okay, so you can see now we have a nice pandas data frame. We have the date here, indexing everything. And then what do we see? We see the highest value of the stock on that day, the lowest value of the stock on that day, the value of the stock when it opened, the value of the stock when it closed, the volume, so the number of trades that were made on that stock, and also the adjusted closing value This is just to account for things like, when they will split a stock, right? Create twice as many stocks for half of the price, or they'll pay out dividends. There's a few events like that that would mess up the data. So the adjusted close takes into account any of those things. Okay. Okay, so let's see how we're going to visualize this. So we have our data frame, so we can access a specific column by the data frame on this variable adjusted close, and that's the main one that we'll be looking at for the value. And then we can call this dot plot function, and it will just plot the data as you see. Okay. Now, and this is kind of handy because note that we have the correct date showing across the bottom, and because that's because this data frame is like indexed by time, so it knows to plot it against that index. Okay, so usually we want to make comparisons, just like in statistical inference. So we might be interested in comparing a few different stocks to each other, or also to sort of like the market baseline as measured by the S&P 500 or something along those lines. So let's see how we would do that. So now I'm going to get a little bit more data. I'm also going to get 2 additional data frames for Microsoft and for Google by doing that exact same function call that I did before. So here in this syntax, I'm going to, because of the structure of this for loop, I'm going to be outputting a tuple, and then each individual value will be a data frame. Okay. Okay. And so I get these new data frames in the exact same way, like for Apple. And then what I'm really interested in is kind of comparing the adjusted close for those 3 stocks. So I'm going to make a new data frame that I'm just going to call adjusted close, new pandas data frame, and I'm going to make an Apple column, a Microsoft column, and a Google column with the adjusted close for each of those stocks. So let's see what that looks like. So you may remember this is the syntax that you can use for defining a new data frame with those properties. Okay, so now we have this data frame that we're going to be working with, which has our 3 different stocks in it. And we can plot that whole thing, right? If we do that, we have these 3 different columns. It's going to plot all 3, and it's going to just label them automatically. That's also nice. But this plot is a little hard to look at. Why is it a little hard to kind of assess, to compare these stocks? That's right. And that makes the plot really hard to read, right? When things are on a different scale, it's really hard to read the plot. So Google is kind of dwarfing the others. And so we can't really see them very well. And when it's plotted on a different scale like that, it also looks like the Google, well, it's much larger, and it also looks like it's much more variable because you see all of the spikes. But that may not be true if it's plotted on the right scale, right? The spikes are looking large because the whole scale is large. Okay, so one thing that you could do is, well, Google's kind of on one scale. These other 2 are pretty close together. So you could create a secondary y-axis that is automatically scaled based on these 2 variables. So that's what we do here. Same function call, adjusted close.plot, but now we're saying make a secondary y-axis for the Apple and Microsoft columns. And so we then will see the first y-axis is the scale for Google, and then the second y-axis over here on the right is the scale for the other 2 stocks. This is a bit better, right? We can now, it's a little bit easier to compare the stocks with these different axes. But it's still not perfect because, well, we may want to compare 10 stocks, and we may have like several different scales, and we can't do 10 different y-axes. So even though this is better, it's probably still not what we really want. What do you think would be a good way of trying to get everything on the same scale? So like take a log of everything. So that might help decrease some of the differences. But if things are on a different scale and you take the log, they'll still be on a different scale, actually.
Could you convert to a percentage increase?
Yeah, right. So you could convert to a percentage increase, and then it's kind of independent, right, of the scale. So that is what we think about doing here. Basically, just take that whole column of data and just divide by the first value. And then you're going to see what each number is as a percentage increase from the starting point. Okay, so we can call that the return at time t will just be the price at time t divided by the initial price. So this is the percentage increase since the beginning. Okay, so that will definitely make comparisons easier. So we need to create some new columns of data where we do that normalization, where we divide by the first value. And one way that you can do that is to define this new data frame that I'll call stock return by taking the adjusted closed data frame and applying this function. Here, just like we saw in some of our other lectures, I'm using a lambda function, which is a shorthand way of defining a function. But what is this doing? It's defining the function which maps x to x divided by the first entry of x. And then it's applying that function to this data frame adjusted close. Okay. And so then if we do that, we can see what we get. Now, notice the first entry of everything is 1, 1, 1. Everything starts at 1. And then we interpret what we're seeing as percentages moving forward, right? On day 4, the stock is up 3.7%. Okay, so now let's take a look at the plot. Okay, and so this is even better than what we had before in terms of making comparisons. Okay, so we can see how profitable each stock was since the beginning of the period. And now it also becomes a little bit more clear that the stocks are highly correlated, right? So notice here when Apple dips, you see dips also in Microsoft and Google. In this portion where it's on a steady increase, these are as well. We do see a lot of correlations between these stocks. Okay, and there's actually like lots of different ways that you can kind of manipulate these things and visualize them. Another thing you might want to look at is like the daily percentage increase instead of since the very beginning of time that you're looking at. You might want to do this. What's the increase at time t? You might want to take the change in the price divided by the price at time t. And so this is kind of telling you, what the increase is for that time period. And then someone mentioned logs, and that's also something that people look at a lot. It's just you do the log, say, after taking this ratio, after converting it into a percent, then take the log. And that's actually a really helpful thing to look at and interpretation. Both of these things are kind of getting at a similar idea of analyzing the increase during time t and the change during time t, just kind of different ways that you can look about it. Okay, the log change is nice. So what are we doing here? price t divided by price t minus 1, if price t minus 1 is, right, think of that as like, that might be something like 1.06 if the stock went up 6% in that day. And so it's basically converting from like the percentage, taking the log of that. These things will be sort of close to 1. Once you take the log, those things will all get close to 0. Okay, so this has some nice characteristics. If we sum up all the log differences, this can be interpreted as the total change over the period summed. And there's some nice connections with modeling things in continuous time. So let's do this too. Let's create another data frame, which is the stock change, computing this log difference. And we can do this in the same way by applying a lambda function. Slightly more complicated here because we're not just all dividing by the first entry. What we have to do is map entry x to the log of x. Sorry, actually you should think of this as like series or list x to the log of x minus that same series shifted by 1, the log of that same series shifted by 1. So shift 1 is going to move it all, one unit. Okay, and so as you see, well, it can't compute that thing on the first day because there's no, when you shift it, you just get like out of range. But after the first day, you can do this and compute this log change. Okay, so let's take a look at what that looks like. So here it looks, yeah, it's interesting now. Now we kind of have things centered on 0, and that's because we took the log. And it looks quite spiky, but this is a way that we can sort of get at something different than what we were looking at in our other plot. In our other plot, we were looking at, well, what's sort of the total percent increase or decrease since the beginning. This is going to be zeroing in on like daily changes, right? When we see a really big spike here, there was like a big daily increase, but the stock could be up or down, like we don't know. Okay, so this is helpful more for looking at kind of what's happening on a daily basis. Okay. But we sort of lose the overall trend. I think maybe it's feeling like it's time for a break. I was kind of waiting to get like to the end of this section, but it just kind of keeps going and going. So let's take a little break. Let's do 5 minutes and we'll come back at 4:30.
So I don't know why, but I cannot install the Panda data reader.
What did it say? Okay, so it says that command pip not found.
Yeah.
Right, so what do you need to install to do a pip install? Let's try Googling it. Cool. Yeah, I don't know about that.
So,
That is weird. Go away.
use the ESC.
There we go.
Cool.
Haha. Yeah, I guess you have to have pip installed in your system before you can do like pip install. So maybe there's another way to install it otherwise you probably have to install the pip first. So let's see. You don't have to install because did you try pip 3 instead of pip?
What purpose, right?
Yeah, I don't know if that's going to work, but let's try it.
Oh,
Okay, it looks like that's working.
no.
No.
Um, Okay. Nope. Yes.
Yeah, let's see. So what happened when you? Yeah, and I don't think we're using Python 3, right? I think we're 2.9 because of the Anaconda installation. Can you try just installing that?
So, easy.
Yeah, I
Slash.
think we want this in Python too.
Oh, this is possible. Wait, what?
But again, this is one of those, if you don't have easy install installed, then you have to install easy
Yeah.
install. So yeah, I may go in a chain from there.
Ah, my God.
Oh, trouble with the password.
Yeah.
Okay, we have a comment in the chat. You want to check environment first. Feel free if anybody has any suggestions or has run into a similar issue. So we've got someone trying to do the pip install and pip is not installed on their computer. So yeah, I'm sorry about that. Maybe we can take a look after class.
Okay.
Let's see if we can figure it out.
Yeah. Thank you.
Yeah, no problem. Okay, so yeah, and then we have another comment in the chat. If you are in base environment, pip should be installed. So just to see, who else is having an issue when they try to install the Pandas data reader? Anybody else having an issue?
I haven't tried it yet.
You haven't tried it yet. Okay. I'm just not yet. Okay.
Are you saying that you're having an issue installing the Pandas data reader?
A student is having an issue with that. Yes, it worked fine for me when I did it, but
You have to type in, so go to your terminal and type in PIP and then space install space Pandas data reader. And then like restart your terminal and then it should work. because I had the same issue.
Sorry, guys, again.
Oh, you want them to say it again? I think they would like you to repeat that if you don't mind that.
Yeah, well, I'll just type it into the chat if everybody.
Okay, great. And I think we're going to take a look also after class and see if we can sort this out. But yeah, if anybody else has encountered a similar issue or still having issues, I'm pretty sure that's what you did though, right? Didn't you do that? That same command?
You have to do it inside the Jupyter terminal, it's with like your actual.
No, your actual terminal. Yeah, your actual computer terminal.
And you have a Mac, right?
I do.
And are you using a Mac too? Is that a Mac?
Oh, you know what? I should have looked. Sorry, what are you working on?
My book.
Yeah, it is. Okay, so it should be similar. Okay, and someone is suggesting to close out of all Jupyter notebooks and then do it. But I think the error he was getting, it was that like pip was not even installed. So I'm not sure if it's. Yeah, exactly. I think that is the problem. Okay, so in the interest of time, I guess I'm gonna move on here. Feel free to keep chatting about this, but if I will, why don't we wrap up the material and then I can try to help with that after class. Okay, so all right, so we talked about some ways of making these visualizations. So one thing that you might be interested in doing is comparing stocks to the overall market. For example, SPY, this is a ticker symbol for the S&P 500. And so you might want to sort of see how is your stock doing relative to the market baseline. And so to compare with that, we can pull the data for this SPY. And once again, use Yahoo as a data source, same starting and ending time. And we can take a look at this tail. So this is all the same as before. Now we're just kind of looking at the market baseline. And I'm gonna just add a new column to all of the data frames that we already have, just adding on the information in this SPY. Okay, so we're adding the adjusted close. We're gonna add the stock return, but this is all just the same thing that we already did. Now we're just gonna add one new column for that value. Okay, and so now we can look at the stock return with the market baseline, right here in the gray. So what do we see? I guess we see that overall, all three of those stocks are performing pretty well relative to the baseline, especially in recent years, right? They're kind of well above the baseline. And oh yeah, here we're also just sort of plotting this baseline starting point where we're computing everything here as a percentage from that initial time. And so it's all like, you know, the increase from 1, which is the baseline. This is just also telling you the line width. That's all, how thick you want the line to be. Okay, so let's also add it to our stock change. We get that 4th column there, and we can update our plot for the log of that change. I'm sorry, that change is defined as the log. So we update our plot with that information. And it does seem like in terms of these daily fluctuations, those 3 stocks seem to have some bigger daily fluctuations than the baseline, which makes sense, right? The overall market is not going to fluctuate as drastically as individual stocks. Okay, so as we do this analysis, of course, the thing that people are really interested in is when do you buy and when do you sell, right? So looking at the historical pattern and making a decision about when to buy and when to sell. So what are some, like, I don't know, things that would be important in making that decision?
Make sure that you're selling it.
Yes, right. You want to sell at a higher price than you bought. You guys remember from calculus talking about rates of change and derivatives? Yeah, so, the derivative is telling you how quickly something is increasing. And so ideally, yeah, you're going to want to, you want to buy at a higher price than you sold. And so you might think that, okay, yeah, it seems like some of these strategies would be related to derivative. When is the stock going up? When is it going down? Even like the shape, the concavity, is it kind of bottoming out, right? Things like that. Those are all related to derivatives. If you look at stocks like this, can you take a derivative there? Meaningful one, because it's so spiky. When you have these like sharp spikes, if you try to like do a difference quotient for the derivative, it's just going to be garbage, right? It's just too spiky to compute a derivative. So the basic idea of trying to do some analysis on this is we need to smooth things out, right? We're seeing a lot of spikes, we're seeing a lot of noise. It's hard to develop strategies based on that because, for one, we can't even accurately compute a rate of change. So one thing that you can do is look at a moving average. So let's say we have a time series, x of t. We can define the Q-day moving average at time t in the following way. We're just going to add up. We're going to take an average of the last Q time points, right? Add them up and divide by the total number. So we're going to replace an individual value with an average computed based on data going Q days back in the past. You can do this in pandas with a rolling function. And so let's try it with, say, a 20-day moving average for the Apple stock. Okay, so we're going to do Apple, create a new column in the Apple data frame, which is our 20-day rolling average. So we're going to make this by looking at the adjusted close column and then applying the rolling function with a window size of 20. Center is false because we're going back in time for this average because we never want to assume that we have access to what happened in the future. And then we're going to take the mean of that rolling average. So when you do the rolling, it's actually going to make those like 20 different data points. And then when you take the mean, it's going to average them. Okay, so what we see when we do that is, well, for the first 20 days, is going to be nan, right? Can't compute it because it can't go 20 days in the past, but that's fine. Starting with this day, we actually get that rolling average that we're interested in. Okay, so let's take a look now at this, comparing the adjusted close for Apple with the 20-day rolling average adjusted close for Apple. And so what we see here, right, much smoother, right? That really smoothed it out. So we see the same overall trend, but a much smoother representation. So it's a little bit easier to kind of talk about when is the stock going up and down and when is the curvature changing and those kind of things. You do notice a little lag though now, right? In general, it looks like the blue line, the 20-day average, looks a little bit shifted in front of the red line, which makes sense because we were, doing these averages back in time. So you're going to see this little bit of lag in the patterns between the blue and the red. Okay, so we see here that it's smoothing the time series, and this can make it easier to identify trends. And so now we've got a parameter to play with, right? The larger the Q, the smoother it's going to get, but it's also going to wash out information that might be important, and it's also going to make the lag bigger. So, you know, there's a little bit of an art here as to what the right way to look at it is. Okay, so ideally, what do we want to do? We want to choose the Q large enough so that we can smooth out those rapid fluctuations, which we think of as noise, but not so large that we wash it all out and create a really big lag. Okay, so let's maybe take a look at some different options here. We can do a 20-day rolling average, a 50-day rolling average, and a 200-day rolling average. And so here, okay, so we had already seen the red and the blue. Now we're adding the purple, which is that 50-day. And we're adding the gray one, which is the 200-day. The 200-day is clearly over smoothed, right? We've really kind of lost everything. Okay. Okay, so now we can start to talk a little bit about trading strategies and back testing. Oh, let me just check if there's anything in the chat here.
I have a question.
Yeah, go ahead.
So on that, which of those would you consider to be smooth enough? Or if you were doing this, like which one would you choose to use?
Yeah, good question. Either the blue or the purple looks smooth enough to me in terms of like, you know, being able to talk about derivative. I don't know, maybe the purple though, because you still have kind of a bit of these fluctuations here in the blue that are not over a very long period of time. It could also depend on what your goal is, right? Are you looking for like a long-term yearly investment strategy, or are you looking to like make these like fast daily trades where you're trying to make a profit in like, you know, a week? So I think it would really depend on what you're, yeah, definitely different types of windows would be useful, I think, in different settings. Right, so in different settings, you develop different trading strategies. So the practice of buying and selling, trying to make a profit. And sometimes these can get very complicated, but we can actually talk about a pretty simple strategy that we already have all of the tools to implement. And this is called the moving average crossover strategy. So what's the idea here? The idea is that we have two moving averages, a fast one and a slow one. When the fast moving average goes on top of the slow moving average, we want to buy the stock. And then when that fast moving average goes below the slow moving average, we want to sell it. So let's take a look here at this picture so we can kind of get an idea of what's going on here. Let's take the blue one. So our blue one is fast and our purple one is slow. So we would want to buy when blue crosses purple going up, right? So maybe we would buy like right here at this point, and then we would keep the stock until the blue crosses purple on the way down, and then we would sell it here. And so notice if we did that strategy, we would buy here at this low point and we would sell at that high point. So that actually tends to be a pretty simple strategy you can do in terms of rolling averages, where you'll usually see a nice increase. Okay, so that's one you guys could actually try. Okay. And then whenever you're trying to evaluate the quality of a strategy, you want to do what's called back testing, right? You want to just take that strategy and apply it to historical data and see if you would have made money. So you can, sort of have some ideas, develop a strategy, then go back test it by applying it to historical data and see how well it would have worked. There is also a lot of built-in Python packages for doing analysis, similar analysis, and here are some of the different options, right, that I think have some of these strategies like built in. Okay. Any questions on that? Okay. All right. So the last thing that we're going to talk about in the last few minutes of class is another really important aspect of time series analysis, which is utilizing frequency information. Okay, so we're going to talk about the time domain versus the frequency domain. So far, we've been thinking about time series as, sequence of times, and then we have a sequence of values associated that were measured at those times. But sometimes it's useful to take that same data series and map it into the Fourier domain. So to think about what are the frequencies associated with that underlying time series. So for example, if let's say we had a function x of t, which is the cosine of 2 pi times ft. So you might remember that cosine is this nice periodic thing. It's oscillating, going up and down. And we can adjust the period or the frequency by changing, the constant in here. This one would have a frequency f for period 1 over f. So the idea behind frequency analysis is that there's different ways to express a function. And one way that we can do it is to sort of measure what's the frequency component at each frequency, and then write it as the sum of those different frequency components. So like for this function here, it just has one frequency, which is just f, because it's this pure thing, just this one frequency. In general, you're going to have like more complicated things. You may have like a long-term oscillation on top of like short-term oscillations and all kinds of things going on. And then you're interested in kind of analyzing which frequencies are present in the signal. Okay, so if you have a signal that's defined on a compact interval, like on the interval, say 0, 1, you can express it as a Fourier series. But basically what you should be thinking of is this little part is just a function with frequency n, and then this is telling you how much of that, how much frequency n you have in your signal. And so you're just summing up all these different frequency functions based on how much of it you see in your signal. And also if you have a signal defined on the whole interval, you can express it as an inverse Fourier transform in the following way. Okay, so we're not going to go into a whole lot of details there. There's so much that you can study, about decomposing things into their frequencies and all of that. So not to like scare you with that, but it's good to be aware of this alternate way of looking at things, where instead of just looking at the signal as it was originally measured, you convert it into its frequency information and look at that instead. And so one way that you can do that is by the power spectral density or periodogram. So this would be take the Fourier transform of the signal and then just look at the squared magnitude. Okay, so this is, if you look at this thing, when it has large values, it means that you have a strong frequency component at f. And when it has small values, it means you don't have much of a frequency component at that frequency. Okay, so let's maybe think of an example, because I think that will be helpful. So there's lots of time-dependent signals that are periodic, right? Where there's some kind of cycle going on. For example, if we have sunspots, these tend to follow an 11-year cycle. So if we had x of t, which is a time series representing the strength of the sunspot, we would see that this thing, the square of the Fourier, the magnitude of the square of the Fourier transform at that frequency f would be large, okay, when f was 1/11. Okay, so if we have a natural period of 11 in the data, then we're going to see a large Fourier value for 1/11. Okay, so if you have like an 11-year cycle, this will be large for 1/11. And also think about temperature. Temperature is a great example because it's really obvious how you get different frequencies, right? You have daily fluctuations as the temperature goes up and down each day. So you're definitely going to have, a frequency of a day, but you also have yearly fluctuations as you have the changes in the seasons. So you basically have like a slowly changing, you have a rapidly changing thing on top of a slowly changing thing. And so you'll see different frequencies present in your data. You'll see like a daily frequency and a yearly frequency that are both significant. Okay, so one way that we can actually compute these things is with the SciPy function periodogram. So let's take a look with some measles data. And this is taken from the course notes, which are credited there. Okay, so first we're going to download this monthly measles data from New York City between 1928 and 1964. This data is inside the lectures folder, and it's just reading from that data file with our pandas.read CSV, right? We love this function after suffering through the last homework. Okay, so this just creates this lovely data frame for us. Okay, so what do we see? We see date here in this column, and then the number of measles cases in this column. Well, what kind of fluctuations or oscillations would you expect with a disease like the measles? Any ideas?
Spikes for outbreaks.
Yeah, you might have spikes for outbreaks for sure. And I don't know if those would be at some kind of regular interval, but definitely seasonal outbreaks, like your outbreak because it got cold, whatever seasonal, the sort of seasonal effect on how many cases you're having would definitely be a thing. So that's kind of what you'll see in this data. If we look at, okay, so first of all, let's just take a look at a plot of this data. So we've got the cases and we're going to plot it. And actually we're plotting it in two different ways. We're plotting it in the simplest way here, but in the simplest way, we don't actually get the bottom axis labeled with the right times. So this would be a little better for getting the right labels on the x-axis. We can just make a list of the date values and plot that against a list of the cases values. And when we do that, we get the following plot. Okay, now maybe a little bit hard to see, but you can see from this data going from 1930 to 1935, right? You've got like peak, 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 peak. There's like 5 peaks in that 5-year period. And it really looks like you're getting a peak like every year, right? Every year you get this peak going up. So these peaks, these fluctuations are occurring at actually quite regular and predictable intervals. So let's see how we could, but if we didn't know that, if we just looked at this time series, maybe we didn't think of that. So one thing that you can do is make the periodogram. So these are the cases from that time series. And here I'm just going to use that function, periodogram, with an input of those cases. This is just saying, like, because the data is given every month, okay, the data was reported as like every month, but if we want to measure things in a time intervals, in a time unit of years, then we would say, okay, 12 data points to 1 year. If we leave that out, it'll just do it in months, and that's fine too. And let's see what we get when we do this. Okay, so here, so this is actually a really interesting plot. So this is telling you the frequency information in that signal. And you see that you have a really strong response at the frequency 1. That's because there's a really strong yearly fluctuation in the data. And then you see a few others. It looks like there's kind of a strong response at around a half, maybe, or maybe that's more like a third. Not quite sure what that is, but you can see a few other points where you see some peaks. Also a little peak at 2 years, which kind of makes it look like maybe if you have like a low year, the next year is a little bit more likely to be large. So that you kind of tend to go from like low to high, low to high. So that could be maybe why you're also seeing a little bit of frequency information at 2. Okay. All right, but clearly the punchline here is that the dominant frequency here is a year, and that makes a lot of sense in terms of the natural oscillations we would expect to see in this data. Okay. And then is it useful to look at the power spectrum of stock data? Try it. So let's see. Yes, it should be useful for sure. Okay, I think, wow, I'm always really impressed with myself when I end right on time. So 4:59. So that's really all I had for the temporal stuff. Any questions before we close out? Okay, well, thanks everybody. Have a great evening and a good weekend. And okay, so I think there was a comment about from one of our TAs. Did you make, first of all, did you make any progress? Did you figure out, or are you still?
Yeah, I still have. I have installed the app, but the problem is like,
Yeah, have a good evening.
yeah, it's like I have installed that, but oops. And after I like have installed the it installs like the same command.
Yeah, I think we tried that, but then I wasn't sure if, because and that worked for you?
It's installed, but but it doesn't work.
So you might want to restart. And also his suggestion was just the same thing with PIP3. Did we try that? I'm sorry, I can't remember. Did you do?
But if you do have Python 3, then that might be.
Great, because in Anaconda we're using 2.9.
Okay. So because my laptop says that it doesn't even recognize the command pip. It's like it doesn't exist. So pip, yeah, it still doesn't work. What OS are you on? Sorry? What OS were you reading?
What do you mean?
The version of your Mac, because that might also
Oops.
change.
It's version 12.1.
12.1. Oh, I don't know that. I'm sorry.
Oh, thank you. That's it.
So let's see. So one suggestion is to do the pip install pandas data reader in the Anaconda prompt. Guess I'm a little unsure.
What?
Sorry, how you want to clarify that a little bit?
Yeah, so what is the error message we're getting?
There is no error message. It's just doesn't work.
When he does pip install the pandas data reader, it's complaining that pip is not installed on his computer at all. So it can't do pip install because pip is not installed on his
I
computer.
have installed the pip, but
He should install the pip first.
Oh, okay, now he's saying that he did install that.
The problem is after I oops.
So now what is he saying?
Where? Oh, Panda, sorry. Okay, it's installed, but after like
Maybe just close out of
okay,
Anaconda and everything. I don't know. It's probably worth trying.
okay.
Close out of is everything closed out?
Yeah. Oops.
That should fade.
Oh, it's no, it doesn't work.
Hmm.
And by the way, I do have oops, not you. I did install the Python 3, but the problem is my default version is Python 2, but I have Python 3.
Yeah, but when you're looking in Anaconda, this version is doing Python 2.7, right?
Ooh.
Do we have pip installed already or not?
Sorry?
What's that? How you?
I mean, do you have pip installed in your laptop?
Yeah.
He didn't, but now he did. So I think he has it now, but it's still and it doesn't give him an error message when he does pip install pandas data reader, but
Mhm.
then he still, when he tries to run the lecture code, it's saying it can't find it. So I'm not quite sure.
Looking for the pandas or?
Oh, yeah, for Python, I was curious that you're on the
Oh, I don't know how.
should be.
Uh, 12.2.4.
Wow, there's so many things in here. Oh, okay, so this is a difference, right?
Okay, so I need
So-
to uninstall Python and reinstall the Python 3.9.
So what I what I think what should be showing there is, let me double check, but I'm pretty sure. Oh, no, sorry, I misremembered. No. I forgot what version we were on. No, just. So that, yeah, so that's,
My version is 3.2.
and did you try doing it with the pip3 command? So pip3 install pandas data reader? Let me try that.
3
Mhm.
dot
No, just pip3 and then install,
oh,
just like you had before, pandas data reader. Oh, no, the whole thing.
oh, pandas reader.
Yes.
Yes. Okay, and I
Let's just try that one more time, like closing everything out,
okay.
because one student was saying that's what he had to do. And so maybe because it's
Oh.
Python 3, I don't know. Pip3. I didn't need to, I don't know, for me, it worked okay when but I'm not sure what the difference was.
Oh,
Hold on, why does?
there.
So
So weird.
here. Why do you have that X there?
Oh, it's a
I don't know what that is.
yeah.
I don't think it's causing a problem. I just didn't, yeah.
Yeah.
Row somewhere in.
I just tried type this in my Jupyter, not the terminal, but in Jupyter, and it works. Maybe try this.
Oh, here, do you want to share your screen?
No, I mean the message in the chat.
Oh, so with the,
Yeah, just with the
okay, let's try. So you mean, but just in the command
just
line,
in- yeah, just in Jupyter, not in the terminal.
your notebook. Okay. Five. Install. It doesn't work. It looks installed something, but after that, the error is no module named pandas did reader. Ooh.
Let's see. I'm not sure. I'm not. So you installed pip,
Yes.
and that should be fine. And it didn't complain. Let's try one thing. Actually, did you restart the kernel? I mean, you restarted the whole thing, so it should be fine. Yeah, I'm sorry. I wish I knew, but I'm not sure. Maybe can you create a
Piazza?
can you create a Piazza
Yeah, yeah.
ticket with this
Yeah, I'm gonna.
and see if anybody else yeah, has suggestions of,
Okay, go.
yeah, I'm sorry.
Yeah,
I'm
it's
sorry, I'm
fine,
not
it's fine.
sure.
Oops.
So I sent another message in the chat, and this is the link for the solution for like no module name pandas data reader. But I mean, I didn't see anything that we haven't tried, but I think this should work normally.
Mm-hmm. So let's see.
Yeah, the only thing he could try is the second response, like just uninstall and install again.
Yeah, okay, so do you have that page?
Wait,
So this might be a good thing to Stack Overflow to look at, because it's exactly the error that you're having, where you pip install the pandas data reader and it doesn't gripe at you, but then it says it can't find it. So, and we may have tried these things already, but maybe read through this
okay,
and see.
yeah, I will post the Piazza, and then could you just leave the link under the comment?
Yeah, you don't have the Zoom open, but yes, I will. I'll do that.
Okay, okay.
Mhm.
Um,
Okay. Okay, thanks, Hao Yu.
Yeah, no problem.
Appreciate that.
Yeah, I wish I could help.
I know.
okay, thank you.
Me too, but we'll get there. We'll figure it out.
I know. Do you know how to post a attach a picture? It's like that. Or
Good question.
because
Details. There you go.
yeah.
Rich, yeah, there you go. Okay. All right. I'm going to sign us off then. Thanks, Hao Yu.
Yeah,